So imagine you are writing a piece of code, right? You test it, and then you realize that just by changing how you store your data, your software suddenly runs like 57 times faster. And that's without even touching the core algorithm itself.
Yeah, it completely upends how we think about optimization. Because, we spend so much time obsessing over algorithmic complexity. But if the physical hardware is actively fighting your data structure, well, all that elegant math is kind of useless.
Totally. And that's exactly what we're getting into today. Welcome back to another deep dive. Today we're looking at this really brutal 2026 benchmark presentation by developer at Lux036, and it's titled Generic versus CSR.
Right, and it's a fascinating presentation.
It really is. The mission for our deep dive today is to explore why your choice of graph representation is basically the single biggest performance lever you have in network optimization.
Oh, absolutely.
We're going to break down the two main contenders in this space, look at this intense stress test, and extract exactly when developers need to drop their flexible tools and just reach for raw, hardware-aligned speed.
Sounds like a plan.
Oh, and for those of you just listening, you can't see this, but my co-host's video background is shifted today. It's this glowing digital web of interconnected nodes. I mean, it literally looks like a cyberpunk transit map.
Yeah, I figured that web is, well, it's the perfect visualization for what we are trying to optimize today. We are talking about processing large directed graphs.
Right.
And in this context, when we say large, we mean networks where the number of nodes, like the intersections on that cyberpunk map you mentioned, is well over 100,000.
So we are dealing with massive scale here, global social networks, telecom grids, maybe supply chain logistics for massive corporations.
Exactly, those types of systems, yeah. And the fundamental operation these networks have to run constantly is called edge relaxation.
Edge relaxation.
Right. In network optimization, edge relaxation is essentially just updating the shortest known distance to a node. So if you find a faster route to a destination, you update your mental estimated time of arrival.
Oh, okay, that makes sense.
You are basically constantly asking the system, can I get to node V faster by going through node U? And doing that millions of times a second, that is the core problem.
Wow, millions of times. So to solve that problem, the presentation lays out two entirely different code-based families stepping into the arena.
Yeah.
Contender number one is built for flexibility and rapid development.
Yeah.
And it's called DiGraphX CVP.
Yeah, and this is the approach most developers would just naturally default to. It uses generic hash maps.
Right.
Specifically, for those of you tracking the C++ details, it relies really heavily on the flat hash map from Google's Abseil library.
Gotcha.
So it uses Python-style iterators. It's heavily templated. I mean, it is incredibly developer-friendly and adaptable to changing data.
But then we have the challenger, which is DiGraphFast. And this one basically strips away all that developer comfort. Right?
Oh, entirely.
It's built purely for speed using a CSR format, which stands for compressed sparse row. Okay, let's unpack this. Because understanding the physical layout of these two structures is critical for you to grasp the benchmark.
It really is the whole ball game.
Right. So if I am using a generic hash map, how is that data actually sitting in my computer's memory?
Well, it is scattered. If you want to find all the connections for a specific node, the processor has to compute a hash, jump to a completely random location in your RAM, grab a pointer, maybe jump to another random location.
Like a chaotic scavenger hunt across a massive city. You find one clue, and it tells you to drive entirely across town for the next one.
Exactly. That's random memory access. It's terrible for efficiency.
Which brings us to CSR.
Right. So compressed sparse row takes all that scattered data and just forces it into a single well-organized sequence. It's like reading a well-organized book cover to cover instead of doing a scavenger hunt.
Oh, I like that.
Instead of relying on hashes and pointers bouncing all around your RAM, CSR stores all the network edges in just 3 flat pre-allocated arrays.
Okay, walk me through those 3 arrays. How do they actually interact if I want to look up a connection?
Sure. So you have the offsets array, the targets array, and the weights array.
Okay, offsets, targets, weights.
Let's say you want to find the connections for node 5. You just go to index 5 in your offsets array. It holds a single integer, so let's say it's 20.
Right.
Then you look at index 6, which is the start of the next node, and let's say it holds the number 23.
Oh, okay. So if node 5 starts at 20 and node 6 starts at 23, that means node 5 has exactly 3 connections.
You've got it. It's just simple math.
Wow.
And because you know those connections sit at indices 20, 21, and 22, you simply slide over to the targets array and read those exact 3 slots to see where the connections actually go.
Right, the targets.
Exactly. And then you read slots 20, 21, and 22 in the weights array to see how much those connections cost.
That is wild. I mean, I never have to search for anything. I just do basic subtraction on the offset index, and I instantly know exactly where to slice the target and weight arrays. It's mathematically beautiful.
It really is the ultimate minimalist filing system. I mean, you aren't wasting time digging through folders. It's all just laid out sequentially.
But, mathematically clean doesn't always mean it wins in the real world. I mean, Google's hash maps are optimized by some of the smartest engineers on Earth. Does this minimalist array actually beat a highly tuned hash map in a real compiler stress test?
Well, the presentation sets up a really brutal benchmark to answer exactly that.
Let's hear it.
They used the MSVC 2026 compiler, the XMake build system, all running on Windows by 64. The test subject is a ring graph where each node connects to 3 forward neighbors.
And that's the k=3 parameter I saw in the source data, right?
Yes, exactly. And the algorithm they unleashed on this graph is Howard's algorithm. Specifically, it's a negative cycle finder.
Okay, for anyone listening who might not be familiar, what is a negative cycle in this context?
Good question. A negative cycle is basically a loop in your network where the total cost or the weight of the journey is less than 0.
Why does that matter?
Well, in financial arbitrage or like certain complex logistics networks, finding these loops is absolutely critical. So for this test, the developer intentionally planted a very specific negative cycle into the ring graph.
Okay, what was it?
It traveled from node 0 to 1 to 2 and back to 0 with a weight of -5 for each jump.
So a total weight of -15. And just to be clear before we get to the speed, both implementations, the hash map and the CSR arrays, they both successfully found that exact cycle with the correct weight. So accuracy is a tie.
Yep, the output is completely identical, but the execution time is where the generic approach just completely falls apart.
Okay, lay the raw results on me.
At a relatively small scale of 20,000 nodes, the CSR format is about 8.1 times faster than the hash map.
Which is a solid win, sure, but maybe not enough to convince someone to rewrite their entire code base.
Right, but let's scale it up. At 1 million nodes, which translates to over 3 million edges, by the way, the hash map takes 176.90 milliseconds to run.
And the CSR?
The CSR format completes the exact identical task in 10.35 milliseconds.
10 milliseconds. That is a 17.1 times speed up.
Yeah, and notice the scaling curve here. As the graph grows, the CSR approach scales near linearly, but the hash map scales superlinearly, meaning its performance gets progressively worse at an accelerating rate the more data you feed it.
Okay, a 17x speed up is massive.
Yeah.
But here's where it gets really interesting, because I have to play devil's advocate here. Nobody deploys bare metal algorithms running in a vacuum in production code bases, right?
Way true.
In the real world, you're using wrappers, separation oracles and abstraction layers to interface with the rest of your system. Does that 17x gap hold up when you add all the messy realities of application development?
What's fascinating here is that that is the exact question the developer anticipated. So they ran a second benchmark using a network oracle, which is a separation oracle wrapper around the algorithm.
And what happened?
The introduction of that abstraction layer doesn't just maintain the gap. It actually causes the hash map's performance to absolutely implode.
Whoa. Give me the numbers.
At 1 million nodes, the hash map wrapper takes 1,713.21 milliseconds, almost 2 full seconds.
And the CSR wrapper?
30.20 milliseconds.
Wait. It went from a 17 times speed up to 57 times.
Yeah.
How does a wrapper make it that much worse? I mean, is the wrapper actively sabotaging the hash map?
It feels like it, right? But it's actually this phenomenon where architectural overhead just compounds. A wrapper isn't a neutral container. It forces data to pass through standard interfaces.
Right.
And the presentation breaks down exactly why this creates essentially a death by 1,000 cuts for the hash map. Let's look at the mechanics. First, distance initializations.
Right.
The wrapper frequently calls operations to set up distances. The hash map requires complex repeater initializations. CSR, meanwhile, just points to a simple vector of zeros.
Okay, so that's cut number 1.
Second, weight extraction. The wrapper doesn't just intrinsically know the weight, it has to actually ask the underlying structure for it.
Makes sense.
With the hash map, the wrapper has to execute a callable function and perform multiple hash lookups every single time it needs a weight. With CSR, the wrapper just reads a pre-computed vector. It's practically instant.
Wow. Okay, cut number 2.
And then there is the cycle extraction itself. When the wrapper extracts the negative cycle it found, it is entirely blind to the hash map's internal memory state.
So what does it do?
The hash map version is forced to allocate entirely new vectors every single time it's called. The CSR version, on the other hand, allows the wrapper to simply reference an internal buffer that was already sitting there.
It's not just one bottleneck then. It's like
Wow.
every single step of the wrapper process is inherently slower in a hash map because of how it obscures memory, and those slowdowns just multiply each other.
Exactly, they compound.
You're turning a 30 millisecond background task into a 2-second frozen screen for the end user. I mean, the numbers absolutely prove that CSR dominates at scale. But I want to dissect this even further. At a microscopic physical hardware level, what is actually happening on the silicon that makes the hash map stumble so badly?
Well, it really comes down to memory access patterns and the harsh reality of a cache miss.
A cache miss.
Yeah. Remember the scavenger hunt analogy we used earlier? Bouncing randomly all around RAM?
Yes, driving all over the city.
Right. Modern processors are designed to predict what you want to read next. When they pull data from your slow main RAM, they load a whole chunk of it into the ultra-fast local cache on the CPU.
Hoping you'll need it.
Exactly. So if your data is contiguous, like our CSR arrays are, the processor's prefetcher notices you are reading sequentially. It proactively loads the next chunk of the array into the fast cache before you even ask for it.
Oh, that's smart. But with a hash map, access is completely random. So the prefetcher is basically useless.
Completely useless. The processor checks the fast cache, it doesn't find the data, and it has to halt operations to go all the way out to the slow main RAM. That right there is a cache miss.
Okay.
The presentation actually calculates that at 1 million edges, the hash map experiences roughly 1 million cache misses.
And a cache miss, in hardware terms, is incredibly expensive, isn't it?
Yeah.
We were talking about, what, 100 nanoseconds per miss?
Yep. Which means those 1 million cache misses generate an automatic 100 milliseconds of just purely wasted time.
But that is wild. You're taxing your system 100 milliseconds just to find the data before the CPU executes a single mathematical operation.
Yes.
When the entire CSR algorithm finishes the whole job in 10 milliseconds, that 100 millisecond tax is just fatal.
It is the defining difference. And the presentation highlights a second hidden tax the hash map pays, which is memory allocation.
Right.
Requesting RAM from the operating system is a really heavy process. Howard's algorithm, when you implement it in a hash map, often ends up allocating memory on every single iteration of its inner loop.
Because it can't predict its own size needs in advance.
Precisely. It just keeps going to the OS asking for more space. CSR, on the other hand, is completely pre-allocated. It asks for all the space it will ever need right at the very beginning, before the critical inner loop even starts running.
That makes perfect physical sense. But there was one detail in the presentation regarding memory that really threw me for a loop, and I want to make sure we get into the mechanics of it. It's about how the algorithms track which nodes they have already visited.
Ah, the visited array.
Right. The source states that hash maps require an order of V cost to call a clear function and reset their tracking. But CSR uses an order of one epoch-based tracking system. Wait. How do you clear a massive list of visited nodes without actually taking the compute time to clear it? Because that sounds like magic.
I know it does, but it isn't magic, it's just a really clever manipulation of integers.
Explain it to me.
So normally, developers track visited nodes with a Boolean array, just true or false. If you want to reset the algorithm, you have to literally iterate through the entire array and change every single true back to false. And that takes time.
Which is that order of V cost.
Yes. But in the CSR implementation, instead of Booleans, they keep a contiguous array of integers and they introduce a central epoch counter for the entire system.
Okay.
So on the first run, the epoch is 1. When they visit a node, instead of writing true, they just write the number 1.
I'm following you.
Then, when that run is over, they don't clear the array at all. They just increment the central epoch counter to 2.
Oh.
Right. Now, on the second run, they check a node. If it has a 1 written on it, but the current epoch is 2, the algorithm instantly knows that node hasn't been visited in this current run.
Oh man, I see. You aren't deleting the old data at all. You are just changing the validation criteria. It's like a hotel keycard system. Think about it. When a new guest arrives, management doesn't physically replace the locks on the door. That would take forever. They just change the digital epoch, right? The code the door accepts. The old guest's card still exists. It just doesn't work anymore.
That is an excellent way to conceptualize it, yeah. Epoch-based tracking is just a beautiful example of mechanical sympathy. You're writing software that fundamentally understands and exploits the physical realities of the hardware rather than fighting it.
So, with this technical autopsy complete and CSR winning by a landslide 57 times over, what does this actually mean for developers? Should we just purge hash maps from our code bases entirely?
Well, that is the ultimate developer's dilemma, because despite these brutal benchmark numbers, the presentation does not declare hash maps obsolete.
Really?
No, it actually lays out a very clear, pragmatic decision matrix.
Okay, let's run through it then. When is the generic hash map approach still the right tool for the job?
You use the generic hash map when your graphs are relatively small, and specifically under 10,000 nodes. At that scale, the processor is so fast that the cache miss penalty is basically negligible. You also need it when your node IDs are sparse or non-integers, like if you're using text strings or user IDs instead of sequential numbers.
Because CSR physically demands sequential integers to make those offsets work, right?
Yeah, it completely breaks without them. And finally, you use hash maps when development speed is your priority, or if your graph structure is highly dynamic.
Meaning things are changing a lot.
Exactly. If nodes are constantly being added, deleted, or shifted in real time, rewriting those three flat CSR arrays over and over again becomes incredibly expensive.
So hash maps are for messy, fast-changing, maybe early-stage development environments. But you reach for CSR when what?
You use CSR when your graphs cross that 10,000 node threshold. You use it when you are optimizing a performance-critical inner loop that runs millions of times.
Right.
You use it when your graph is static or only incrementally built, and most importantly, when cache efficiency is paramount. The presentation actually gives a really clean rule of thumb here.
The 1 millisecond rule.
Yes. If your graph takes more than 1 millisecond to process, the time investment to convert your data into CSR will easily pay off.
You know, if we connect this to the bigger picture, where does this structural optimization go next? Because once you have your data locked into perfectly contiguous CSR arrays, you aren't just pleasing the CPU cache, right?
Right.
You essentially open the door for entirely new classes of hardware acceleration.
Oh, the future directions outlined in the presentation are thrilling.
Yeah.
Because CSR relies on flat arrays, it is just the perfect match for parallel relaxation on GPUs.
Right, graphics cards.
Exactly. A graphics processing unit is essentially thousands of tiny processors that excel at doing the exact same mathematical operation on a sequential list of numbers simultaneously.
And a GPU would just choke on the random access of a hash map.
Completely. It would grind to a halt. The source also points to SIMD vectorization.
Remind me what SIMD stands for.
SIMD stands for single instruction, multiple data. Because CSR's edges are stored side by side in RAM, a CPU register can actually load 4 to 8 edges at once and process them in a single instruction cycle.
Wow.
Yeah, multiplying throughput natively without even needing a separate GPU.
That's incredible.
Yeah.
There was also a mention in the source of arena allocation to help hash maps reuse memory pools, which I suppose might lessen that allocation tax we discussed. But the concept that really stood out to me in the future directions was the hybrid approach.
Yes, using CSR for the hot paths, like the core arteries of the network that are queried millions of times a second but rarely change structure, and then maintaining hash maps for the edges of the network that are experiencing constant dynamic updates.
That makes so much sense. You get the flexibility where you need it to ingest data, and then the raw speed where it counts for computation.
It proves there is no single silver bullet in network optimization. But understanding how your hardware physically reads memory is basically the closest thing to a superpowered developer can possess.
I think that perfectly summarizes the mission of this deep dive. While hash maps offer incredible flexibility for getting a project off the ground, when you were dealing with massive scale, mechanical sympathy is literally everything.
It really is.
Organizing your data into contiguous memory so your processor isn't wasting 100 milliseconds searching for scattered clues makes CSR the undisputed champion of performance. I mean, you just cannot argue with a 57 times speed up.
The hardware never lies.
It really doesn't. And before we go, I want to leave you, the listener, with a final thought to ponder. Building on that idea of the hybrid approach from the presentation, as our systems grow infinitely complex, could the future of network optimization be an AI-driven, shape-shifting data structure?
Oh, that's an interesting thought.
Imagine a graph representation that starts out as a flexible, developer-friendly hash map during data entry. But the moment the system detects a heavy algorithmic load incoming, it autonomously compiles itself into a cache-friendly CSR array right on the fly.
That would be amazing.
Right. No developer intervention required. Just data that organically knows exactly what shape it needs to be to survive the stress test.
No, that is the future.
Absolutely. Well, thank you so much for joining us on this deep dive. Keep questioning the defaults, keep optimizing, and we will catch you next time.